choose the coefficients to have walls of longer length weight less than walls of shorter length. And the coefficients that define the Mittag-Leffler function are not monotonic for all the values of alpha. So I need to put a restriction on the gamma to maintain the monotonic behavior I want. It is not too difficult to prove that if you choose a gamma that is in between these two values, you retrieve the monotonic behavior you are looking for. So in a way, you fix the model in this way. And there is still another problem, but this one is instead computational. As I've said before, I'm looking at matrices that have no loops, so their trace is 0. And this means that I've got both positive and negative eigenvalues. For example, this is a social network of dolphins. And if you plot the eigenvalues of the adjacency matrix, you see that you have -1, no problem, and some +1. But Mittag-Leffler function is explosive more than exponentially on positive values. So this may be a problem. So we have already seen this in the plenary this morning. But the idea is that you can use the asymptotic expansion for the Mittag-Leffler function to also find a value of gamma that actually permits you to compute these quantities on the machine you have. So if you have a machine that can represent at most this number, you can choose an apt value of gamma to obtain a number of your machine. So wrapping up all the definition, what I do is I take the minimum in between the two conditions, and then I can define both the subgraph centralities and the total communicability in terms of the Mittag-Leffler function. Now we have solved part of the, let's say, the modellistic part. Then we need to actually compute these two measures. So I'm going to use the techniques and the code developed by Roberto and Marina that solves the problem for small matrices. Then you have to solve it for large matrices, and for this one, the route is exactly the same that what Igor was talking about. So you go to Krylov methods and do projection. So big matrix, small matrix. For small matrix, we have the solution, and then we project back. I won't go into much more detail about this because I know that Maria is going to talk plenty about this next. There is a slight also difficulties if you want to compute the subgraph centralities for all the nodes, because you have to do, let's say, n number of nodes matrix function evaluation. So this could be quite expensive, but there are methods based on the link between Krylov subspace projection and quadratures that permits you to reduce the amount of computation and catch only the important part. And let me show you that the convergence result applies. So this is on a standard machine, so with IEEE 745 arithmetic. And as you see, if you go outside the range given by the representability, you get none. And if you go outside what is modeling available, you don't lose much because the function is actually continuous. So even if you're breaking the model, you are not losing completely the behavior. And as you see by the color coding, when you move with alpha, these are correlation coefficients between the degree centrality and the eigenvector centrality. If you move with alpha, you retrieve the limit behavior. And similarly, if you move with alpha, you retrieve also the correlation between the degree centrality and the eigenvector centralities. So let me see if is it moving? Oh, is it moving? Okay. one can look also at network that evolves over time. So we have a fixed set of nodes and edges that move. So this means that instead of having a fixed adjoint matrix, we have one that depends on time. So we may want to do the same procedure here. And the idea is to, from Greenroad and Eigen paper of 2014, is to find a matrix that encodes this information. And the idea is always the one of counting that works that appear until a certain time. So this is just if you write it down, it's just the counting of this work. Particularly, if you take a discrete time step, you recover simply the product of the measures at all time steps. This is the so-called generalized cut centrality, so the one based on the resolvent. But what this entails that you have to put the restriction on the gamma parameter because this thing needs to be invertible. So what's you can get if you put here the substitution of having u equal e plus s, do some Taylor expansion and a bit of computation, you end up having a differential model, and that is a continuous analogous of the previous one, but you still have now to be sure that you can compute this logarithm. So what we want to do is, let's say, instead of having the resolvent here, we put here the Mittag-Leffler function. And what's the idea? So we still want to interpret between the resolvent and the exponential behavior, and we don't want to bother with knowing the full temporal evolution and having to choose a parameter gamma that makes the logarithm computable. So if you plug in there the Mittag-Leffler, you don't need much more information on all the matrices. So this means that this can happen at runtime. You don't need to know them all at the beginning. And let's see if this. Okay, so when you have this one, now you can solve this ODE, but you don't want to actually solve the matrix one. You are interested in looking at the ranking. So you either look at the dynamic broadcast or at the dynamic receive. If W is symmetric, so if the network is undirected, these are actually the same. Otherwise, you're counting in one case the outgoing information and in the other the incoming. So you can look at either of that. And the nice news is that when you multiply here by the all one vector, you get a scalar D. You get a vector D and not a matrix OD. Just to give you an idea, this is a test case in which the network switches in between these states, and in which we have also some shortcut in a random way. And what we observe, again, by the same correlation plot as before, that the measure is much more dependent on the value of the gamma than on the alpha. So you can actually use the Mittag-Leffler to subtract the problem of knowing the dynamics and recovering the information you were looking for. Let me wrap up because I've surely gone out of time. So what are the things that we still want to do? Well, there is a clear connection between Mittag-Leffler function and Caputo time fractional derivatives. So it would be nice to be able of exploiting this information and to interpret the result we get in terms of fractional evolution in time. So like Igor was doing fractional evolution in space, maybe we could do the same thing in time. And maybe finding also a physical model representing what we are computing. So in terms of a network of fractional or quantum fractional oscillators. you can read all this information in this preprint on the archive. Thank you.
Yeah, we have time for a couple of questions. Can you say something about the comparison with the K-path Laplacian in order to, take into account finding some other way?
So for the one of you that are not much into this, the K-path Laplacian, the idea is that I go back to some way I figure with the paths. So you build an adjacency matrix that in a way encodes in the high J entry the length of the path. So it's some way the sum of all the adjacency matrix for all the distances, and look at the values of let's say the eigenvectors and centrality on that one. We didn't actually do the comparison with that one because there are, at least that I know, no relationship between limit relationship on that one. But it could be interesting to look at because also that is an information that encodes all the length possible on the graph. So in a way, also that one is non-local. I would say that they behave at the opposite because that one makes the diffusion go faster while the fractional time make it go slower. So I would expect the opposite behavior. There are some comparison with the fractional Laplacian, and that's a bit of a religion war, which I don't want to get into.
Okay, thank you very much.
Thank you.
Yeah, we have 5 minutes break and then switch to the next speaker.
Okay, we can prepare, yeah. Togliere questo da qua. Forse aggancia la rete wifi, quindi non ti conviene.
Scusa perché non prendo il file responsabilità.
Okay, so our next speaker and the last of this morning is Marina Popolizio from Polytechnic University of Bari. She will present a talk about efficient numerical approximations of the matrix beta-Leffler function. Please, Marina.
Thank you, Maria Rosario. Okay, so this is going to work with Roberto Garrappa and Tiziano Politi from Polytechnic di Bari, and actually we are still working on this. So,
Faccio un clic lì, l'avevo provato.
Okay, so I will start with the definition of the beta-Leffler function, even if we have already seen it in this morning and also yesterday. But just to introduce then the issues that we have in the numerical approximation of this function. So I will start with describing the scalar case, and then I will talk about the matrix case. Then I will show some practical tests and some references. Okay, so this is the definition that we have seen a few minutes ago with Fabio. Okay, so we have these two parameters that in general alpha and beta are complex with the positive real part, and the particular feature here is the presence of this gamma function at the denominator. And it is interesting to notice that it actually generalizes the factorial. So when k is a natural number, actually we have this equality, but in general we may apply this function to more general arguments. And this is an important fact. Actually, when alpha and beta are both equal to 1, it is clear that we have exactly the exponential. But as soon as we move from these special cases, alpha equal to 1 and beta equal to 1, actually we have to deal with the loss of good properties typical of the exponential. Okay, so the name is due to Mittag-Leffler that introduced this function for beta equal to 1, but then it was generalized a few years later to two parameters by Wieman. This function is particularly important in the fractional calculus, and as already seen today, yesterday, etc. We know that this function is the eigenfunction for the fractional derivative, and this is. And so you may see that the solution of this specific problem, differential problem, with this denoting the Caputo fractional derivative, may be expressed directly by means of this Mittag-Leffler function. And so by means of this Mittag-Leffler function, so we are able to better understand the theoretical properties of fractional differential equations, and they are also important in defining numerical methods. And for these reasons, actually, the Mittag-Leffler functions have been defined as the twin function of fractional calculus. And And it is important, it's important is the same that the exponential has for ODEs. And so we know that to study the theoretical properties of the ODEs, we look at the exponential. And so this is exactly the same to better understand the fractional differential equation. Okay, but here I'm talking about the Mittag-Leffler function with the matrix arguments. And so I try to explain the importance of this topic. And the most simple situation is the case in which we have systems of fractional differential equations. And so in this case, so in this case, the solution may be written as the Mittag-Leffler function evaluated in the matrix argument A applied to the vector y0 of the initial condition. So, okay, the interest in the Mittag-Leffler function evaluated in the matrix arguments is related to these systems of FDEs, but it is also important when solving partial differential equations in which we have fractional time derivative, but ordinary space derivatives. And so if, for example, we apply the method of lines, we may first discretize with respect to the space variables, and so we reduce the problem to a system of FDs. And so, as before, we need to compute this Mittag-Leffler function in the coefficient matrix. But this matrix formulation actually is important also in the context of controllability and observability, which is very important in control theory and so for all the engineering applications. And here that's another example for multi-term fractional differential equations. So we have when we have a differential operator with several derivatives of fractional order. Okay, so I just give you an idea of a numerical method that we may describe by means of the Mittag-Leffler function. And we have this problem here with A times yt plus a linear term f of t. So by means of the variation of constant formula, we may write the solution in this form. And so we have here the Mittag-Leffler function and this term f. The idea of the generalized exponential integrators is to apply polynomial approximation here in the integral, but just for the term big F, while in general, a similar approach has been applied to all these terms. But in this way, so working just with f of t, actually we get excellent stability properties, high order convergence, and in some sense, we overcome memory issues because, as said a lot of time in this workshop, here the definition of, for example, here the presence here of this integral tells us that the memory is important, and so actually we need to take into account all the memory, all the past, or what happened between 0 and t. But here, if we rewrite the numerical approximation in this form, we see that actually we just look at what's happening in Tn. So if we are interested in the solution of Tn, actually we go directly at that point. The memory is here in the Mittag-Leffler function, and so we may compute this solution, whatever is Tn, with so also in a very large interval. The computational issue here, okay, is the computation of this term, these Wnk, which are a linear combination of the Mittag-Leffler functions with indices alpha and alpha plus k, evaluated in a scale version of the matrix A. And okay, you may appreciate here that actually we need to compute several matrix functions, these Mittag-Leffler functions with parameters alpha, the second parameter alpha plus k that changes for the same matrix A. And in the approach I am going to describe, we will appreciate that actually this computation will be reduced and addressed in an effective way. Okay, and then there is the application that Fabio discussed a few minutes ago. And so the matrix Mittag-Leffler function is important also in the network theory. And in fact, in its definition, okay, we have seen this, and so probably you recall this definition. We have this adjacency matrix of a simple graph, and so we define this Mittag-Leffler subgraph centrality. It requires the computation of this special Mittag-Leffler function in which beta is equal to 1, but it's not a problem, evaluated in this matrix gamma A. Okay, Fabio discussed the role of gamma, but for me the important fact is that here we have a matrix argument. And actually this also justifies the interest that we have here in the special matrix arguments. Because, for example, as in network theory, the argument matrix A has usually a large dimension. In common applications, it has a small rank or fast decaying singular values, and it is sparse. So I'm going to address now the problem of matrix function computation with this hypothesis on the matrix argument. The key idea is actually to reduce the problem. So we do not compute the Mittag-Leffler function E alpha beta of A, but actually we just compute E alpha beta for a different matrix M that is in general much smaller than A. And S1, S2 depends on the approximation we consider, but okay, this is the important fact. The idea that we compute a matrix function, but with a much smaller argument. Okay, so in the hypothesis of a large matrix with small rank or fast decaying singular values, a good and effective approach is this sparse column row approximation. It was proposed by Stewart, and the idea is to apply the Coffey-Gram-Schmidt algorithm to A and A transpose. So when we apply it to A, we get a set of representative columns, while to Y transpose, we get a set of representative rows, Y transpose, and then we solve this minimization problem in order to find the matrix P, which minimizes this error in the Frobenius norm. Okay, so once we compute this matrix T, actually we approximate A by means of this product X, T, Y transpose. The interesting fact is that X and Y consist of columns and rows of A, and so they are sparse. So this is a good feature, a good method to work with when we want to preserve to exploit the sparsity of the matrix argument A. And this block T is much smaller than A. Okay, a few remarks on this method. It works, it is particularly effective when A is large but has a numerical rank R, which is much smaller than N, because in this case we reduce this dimension to R times R, and we will exploit this dimensional reduction in the following. And another important fact is that actually we may monitor the error of this approximation, and in fact we may fix an accuracy, say epsilon, and find the T which satisfies this bound. Okay, so our initial goal was to compute the Mittag-Leffler of our matrix argument A, and in here by means of this theorem, actually we express the Mittag-Leffler of the term X T Y transpose as the sum of the identity matrix scaled by means of this factor plus X times the Mittag-Leffler of this matrix Z, defined here as the T Y transpose X, times the T Y transpose. This theorem was originally proposed by Celedoni and Eigen for the exponential, but we have generalized it for the Mittag-Leffler function. You may see here that actually we have reduced the problem. because now we just compute the Mittag-Leffler function in this argument of dimension r times r. And so the objective of having here a small r is to reduce in an appreciable way the dimension of this block. Okay, so in our context, actually, we mix these two factors. So we approximate A by means of X Ty transpose, and so we approximate the Mittag-Leffler of A by means of this combination. And so actually, we reduce the problem to these, the computation of this part. Okay, so this is just the formula before, but I wanted just to stress the fact that now we have to compute, okay, this term, and so this is maybe very effective in the case in which several terms of this form are required, because the approximation X Ty transpose may be computed just once, and so then we just compute this Mittag function for these small blocks. And another interesting feature is that the conditioning may improve, because for the theoretical analysis we are doing, actually it seems that when the second parameters here increases, the conditioning of the Mittag-Leffler function decreases, and so the stability improves. Okay, but we have still to address the problem of computing the function with matrix arguments. And when we started with Roberto thinking about the Mittag-Leffler function with matrix arguments, we considered other methods, but the sure padlet is the one that may be applied to general functions, and it is actually the core of the FUNEM algorithm present here in MATLAB, and so we tried to apply it in our context. The idea, because it is in general efficient and stable, even if, okay, the application was not straightforward for the Mittag-Leffler function. The idea is to start from the sure decomposition of A, so A is written as a Q, TQ star with a Q unitary and T upper triangular. Then, and this is a trick due to Davis and INdAM that actually improved the initial version of this routine. T is reordered in blocks in such a way that each block has clustered eigenvalues and distinct blocks have far enough eigenvalues. And then we start computing the diagonal blocks of this triangular matrix by exploiting these truncated Taylor expansions. And okay, everything, and then by means of these diagonal blocks, we compute the extra diagonal blocks by means of the Padlet recurrence, and then the Mittag-Leffler of A is computed in this way. The challenge here is the computation of these derivatives, because numerically there was no method to deal with these objects. But we have to step back, because actually when we started this kind of research with Roberto, we had to start from the Scalar Case, because in these languages there were no codes for the Mittag-Leffler function. There was something on Mathematica, but no derivatives, no matrix arguments, and so we wanted to find a code accurate, reliable, and fast. The fact is that, okay, the expression for the Mittag-Leffler function is simple. You see, you have just this series, but it's not as simple as with the exponential, because the convergence is very slow. So we would need a lot of terms to compute an approximation of this series. But on the other hand, we have this problem with the gamma function, and Fabio also discussed in some way this behavior. And okay, for our machine, actually, this was the largest value admitted, and so catastrophic cancellation can happen, and so this approach cannot be used in general. Also because the semi-group property does not hold, and so we we usually use this property for the exponential, scaling and squaring, and other methods in which you may apply something like this. But in the Mittag-Leffler case, we cannot, and so we had to find other methods. Okay, we compared some techniques, but we found that the most effective one is based on the inversion of the Laplace transform. Roberto described it yesterday, so I just give you the definition. And by starting from the work by Wiseman and Trefethen, actually we generalized this analysis that was just for beta equal 1/2 in the case of the Mittag-Leffler function, but we have generalized for any case, and so we have here this code ML that works in the complex, in the whole plane. And actually we used the same approach also for the derivatives, because also for the derivatives we have some series expansion, but by working with this numerical inversion, we get good results, even if here we have to take into account the fact that the order k of the derivative actually defines the strength of this singularity. So we actually mix derivatives of a smaller degree to get an accuracy, but you can find that all the technical aspects here in this paper. Okay, so if we go back to our Schur-Parlet algorithm, now we have the possibility to compute the derivatives of the Mittag-Leffler function, and so we are able to compute the Mittag-Leffler for matrix argument. And okay, so I just give you now some examples for the hypothesis I did. So in the first example is for this matrix, which represents a directed multigraph. So it has this dimension 953 times 953, but it has rank 155. So then I measure this error by computing the Mittag-Leffler function of the full matrix A and the Mittag-Leffler function of this term by exploiting the theorem we get. And so actually we compute the Mittag-Leffler function with a matrix of dimension 155. And you may appreciate here the accuracy of this approach. So even if here we actually have two kinds of errors, because we have the error related to the matrix approximation and the error related in some sense to the computation of the Mittag-Leffler function, but the final result is very accurate. Okay, here there's another example. This was proposed by Barry, and is a special matrix with logarithmically equally spaced singular values. And so here we have this fast decay of these singular values. This is a very sparse matrix. We consider just a dimension 100 times 100, and just 14 columns are sufficient for the Scalar approximation to have this good accuracy. And so so here, for different values of alpha and beta, we have the error in the approximation, and as before, here actually we computed the Mittag-Leffler function of the Z term that was in the theorem, and we have a comparison between the computational time. Here we have the time to compute the full matrix, the original, the Mittag-Leffler of the original matrix A, while here this time actually takes into account the time to compute the Scalar approximation and the time to compute the Mittag-Leffler of the small term. And you see that you always have one order of magnitude here in saving, and in some cases we have two orders of magnitude in the difference of two orders of magnitude. Okay, this is the last example. We have this matrix proposed by Rubik to describe the initial state of a Bose-Einstein condensate in an optical lattice. The matrix is defined like this. Actually, we have the same parameters that the authors used in their paper. And in this context, you see that R is equal to 2. So just 2 columns and 2 rows. So actually, we have a block 2 by 2 in which we computed a Mittag-Leffler function. The starting error is very small, and we have a very accurate approximation even for the term for the Mittag-Leffler function of the matrix A. Also, in this case, we have here the comparison in time, and so you may appreciate that actually the saving is important. Okay. Yes, these are some references. No, just because with Fabio and Igor talking about the Krylov subspace method, and okay, I have also compared the Krylov subspace methods to the techniques in the case in which we are interested in the action of the matrix Mittag-Leffler on some vector. The results are comparable in terms of computational time and accuracy, but the additional advantage here is that we can directly compute the full matrix, and this is not possible in general with the Krylov subspace. Okay, that's all.
So, comments?
Just a curiosity, if you can explain how the low-rank approximation algorithm works, and for that matrix, and whether you also, so as far as I get, so you have a sparse and low-rank matrix or mega low-rank matrix to approximate. So whether you also try, I don't know, some randomized SVD approach or Lanczos for the approximation.
No, right now I have just used this kind of approach, so it's a quasi-Gram-Schmidt algorithm that you apply to start to select the important columns and rows of the matrix.
So it's like you start with a column, then you
single out
its contribution. Okay.
You follow, and then you see what are important.
So what is the impact on the computational time of this part? Maybe it's kind of cheap.
Yeah, it is cheap. Also because in our examples, actually, the number of columns you have to select is small, and so it stops question.
Okay, thank you.
You're welcome.
Okay. Other questions? Nothing from the chat. I actually have a quick curiosity about the conditioning. You said that the conditioning was decreasing.
Yes.
Can you say something about the behavior of this conditioning? How it's decreasing?
It seems to be monotonically decreasing with respect to the second parameters. But actually, you need some information about the spectrum of the matrix. Yes, to bound in some sense the integral representation of the Fresnel derivative. But in this situation, you see monotonic behavior with respect to the second parameter.
Okay, thank you.
You're welcome.
With no other questions, let's thank Marina again and all the speakers.
We are on fire. We are.
Sorry. Okay, good morning. I am one of the organizers, Marco Donatelli from the University of Insubria, and before lunch, just two advertisements. The first one is about the certificate of attendance that will be ready in a couple of days. We will send by mail a PDF, and so you will receive by mail. And the second one is about the special issue for the contributor to this conference. As you know, this workshop is supported by the INdAM, the Italian National Institute of Mathematics. And so there is a Springer INdAM series that is a special series for the contribution of this kind of conference that, first of all, that is important now is that, of course, is indexed on Scopus, so the volume will be indexed on Scopus, and okay, The organizing committee will handle the review process, and we are planning to, in September, we expect your interest, your interest, and in February should be the deadline to submit the contribute. But we will send you an email with all details, and of course your expression of interest will be useful for us to have an idea about how many manuscripts we should have. And thank you again, and thanks for that.
Thank you.